So in the reading, we talked about, or the reading described adversarial methods from a very kind of like machine learning point of view. As I went back and read it, I realized that it was maybe not described in the most systematic way, so I'm going to try to describe it in a slightly more systematic way here. Although chapter 2 was actually very good at putting it in perspective with other things if you already knew what the other things were. But anyway, I'll go through and explain with respect to NLP and everything. So generative models, as we've talked about before, we have, using generative models, we can either generate a sentence randomly from some distribution or generate a sentence conditioned on some other information using a distribution like this. Actually, I realized I got X and Y backwards here. Usually we have X conditioned on X and outputting Y. But these are very useful. One good thing about the reading was why generative, it asked the question, why generative models? I would have put it maybe a little bit of a different way. There's a lot of reasons why you could like generative models. Some of them are that you can learn about the world like was explained in the reading material. Another one is that you can actually use generative models to do classification, for example. If you train a very good generative model that models the joint probability of X and Y, you can also use that to do classification or whatever as well. One problem with generation, and the main motivating reason behind GANs, is that generative models can create very unnatural outputs if they're not trained well, or if they get in a conditional generative model, if you get an input that you don't know what to do with, really. So this is a very good example. So the real image is on the left. The middle image is here, and this was generated by something using regular maximum likelihood estimation. And then the one on the right is one generated using an adversarial technique. And the thing you notice immediately about the things using maximum likelihood is they're fuzzy or blurred. And this is a problem for images. For text, this can also be basically seen in the generation results when you, for example, take a dialogue system, and no matter what you ask it, it says, I don't know. Like every time you ask it to generate an output, it says, I don't know, and you get a very common result. So one important thing to note about this is if you have a generative model, that's not necessarily wrong, saying I don't know all the time. Because you think about it. If you think about it, in dialogue, there's a lot of variety. And maybe when you say, what is your name? If you say, what is your name? Most people will say, my name is something. But because everybody has a different name, that something at the end of the sentence becomes very, very sparse and spread out. So then maybe there's 1%, or maybe there's 5% of very strange people who say, I don't know, when you ask them their name. But that 5% might be higher than all of the other names in the corpus. So I don't know is a rational answer. So this is a really big problem with regular generative models or that use something like maximum likelihood, because they just try to find the most likely thing. And another thing they try to do is they try to be safe in their output. They try not to predict anything really unusual. And when that happens, you get a very boring output, I guess. So the idea behind adversarial training basically is to create a discriminator that criticizes some aspect of the generated output. You can use this in basically there's probably other ways you can use this, but the way people tend to use this is basically in two different paradigms. One is generative adversarial networks. What these try to do is they try to criticize the generated output. So you generate an output, and then you have a discriminator that criticizes this output and says whether it's good or not. Another thing is adversarial feature learning. So you don't actually directly criticize the output itself, but you criticize the features learned by the model, and then you use that to improve your output indirectly. So these are two different things. I'm going to talk about each of them in turn here. So the first one, which was the topic of the reading, was generative adversarial networks. And the basic paradigm is we have two players, a generator and a discriminator, and to generate natural-looking output. It's the discriminator's job, given an image or an output, try to decide whether it is real or not. And for the generator tries to generate an image or output that that fools the discriminator into answering real. So if we go back to this example, I think the reason why this works becomes very intuitive. If you have a regular maximum likelihood trained model, it will choose to be fuzzy because it's safer to kind of generate a fuzzy image that looks like a lot of other average images than it is to generate a very sharp image and maybe get it very wrong. But in a generative adversarial network, what happens is you have a separate network that tries to measure the difference between this and this. And if the discriminator correctly guesses that the generated image is fake, then the discriminator wins and the generator loses. So the generator's parameters get updated to try to prevent that from happening. So it's very, very easy to tell the difference between these two generated images because one is very fuzzy and the neural network can detect fuzzy images. They're good enough to do that. Similarly for dialogue responses, I don't know is very easy to detect, right? The difference between my name is Joe and my name is John is not very easy to detect. So if you have outputs that tend to look fake, they'll get penalized, or tend to look generated, they'll get penalized. Is that clear? I'll talk about the specific training method next. I should just add that I think this is a really great idea. It's a very, very nice idea, and it's executed very well. So I think it's useful in a lot of places, although I'll explain about some of the drawbacks in a moment. So basically, the training method here is we have our big database. Right now, I'm going to talk about a regular generative model. It's not a conditioned generative model. But we have a database of training examples. Maybe these are sentences in English. Then from this, we randomly sample a mini batch, a sentence or a mini batch worth of sentences. And that gives us X real. Then we randomly sample latent variables like we used in the variational autoencoder. Maybe we sample them from a Gaussian distribution or something like that. And then based on these latent variables, we use the generator to convert them and to generate this X fake. So these are our fake examples. Then we take the discriminator and we predict whether these are real or fake for each of the examples that we generated. And then we have two varieties of loss. We have the loss that's used to update the parameters of the discriminator. And so we do backpropagation, and we go back and update the parameters of the discriminator. Then we have a generator loss, and we do backprop all the way back through the discriminator into the generator and update the parameters of the generator. And the important thing here is basically the discriminator loss will be higher if we fail predictions. So it will try to make the discriminator more accurate, while the generator loss is higher if we make predictions accurately about real or fake. So we have these two competing losses. So you can view the discriminator and the generator as competing against each other. Are there any questions? Okay. Okay. So doing this in equations, the discriminator loss function, this is just the same as the paper. Basically, we want to optimize the expected negative log or our loss function is the expected negative log likelihood for both the data and the generated samples, where D is the discriminator probability, basically the probability of the data being true. And so based on this, we give a high probability. Yeah, maybe on the right, that should be a low probability for fake data. So we want to give a high probability for real data and a low probability for fake data. And then the generator loss function, there were two examples of this shown here. So the first one was the zero-sum loss. So do people know what know about the idea of a zero-sum game from economics or game theory or whatever? So a zero-sum game is like when you go into a casino and you start spending money and gambling. Either you win or the casino wins. Either your money goes to the casino or the casino's money goes to you. And if you add them together, you get zero. So that's called a zero-sum game in game theory or economics or something like that. And the idea here behind the zero-sum loss is your generator loss is the opposite of your discriminator loss. So either your generator wins or your discriminator wins. The second one is the heuristic non-saturating game loss is the name in the reading material. This was a rather grandiose name, but basically what they do is they switch the, let's see. I don't know if that looks right to me. I might have the sign messed up here or something like that. But I think basically the idea here is that you want the probability, or no, that's right. I'm sorry. You want the probability of real to be high for the fake examples, and so the generator wants this probability, the probability of real, to be high for the fake examples. The discriminator wants the probability of real to be low for the fake examples. So this seems like a very kind of small difference, but actually it results in a big difference. And the reason why is because if you think about it, when the discriminator is very, very accurate, if the discriminator is extremely accurate and it gets it almost right almost all of the time, this loss, the discriminator loss will be very small. It'll be almost zero. So if you just treat the zero-sum loss, if you just use the zero-sum loss, that means when the discriminator is very, very accurate, your discriminator loss and your generator loss will be very close to zero, which means you won't get any updates. On the other hand, if you use this one, when the discriminator loss is very close to zero, this loss will actually be very large. So you'll be doing very large updates of your generator to try to get it out of the state where the discriminator loss is bad. So that's the idea of this method. So any questions about that? No? Okay. So there are problems with training. So in general, GANs are a really neat idea. Basically, we want to generate something that looks real, and we can train a network that decides whether it looks real or not. But there are lots of problems with training GANs effectively. And I think a lot of these problems are similar to the problems we have with other methods like reinforcement learning. But one major method that we get with GANs, or one major problem that we get with GANs is called mode collapse. So basically the idea is that the generator learns to map all Z to a single X in the training data. So there was this very abstract example, I guess. There was this very abstract example in the reading material that had like 5 Gaussians and was trying to explain how things converge onto one Gaussian. But just to make it a little bit more concrete, let's say our training data is hi, my name is Graham. I teach at CMU. At CMU, I like peanuts or something like that. And one of these is a lie. But anyway, so this is our training data. And in regular maximum likelihood, we want the ideal, or what is the ideal probability that our model could give to each of these for a language model? What is the best possible like language model probability that we could give to each of these sentences? Any ideas? This is it's not a trick question. The answer is actually pretty simple. Anybody brave enough? Yeah, exactly. 1/3, 1/3, 1/3. So you give an equal probability to each of the sentences, and this is the ideal maximum likelihood solution. The reason why we know this is because the solution that maximizes the entropy of the distribution is basically a uniform distribution over all of the, or minimizes the entropy of the distribution is the thing, is the one that gives a uniform distribution to all of the things in our data. So this, in maximum likelihood, basically we can generate any of these and we'll generate any of them with equal probability. But the problem with GANs in mode collapse is basically what the generator has to do is it has to find a single example. At the very beginning of training, what it can do is it can find a single example that exists in the training data and then generate it all the time. And it will basically continue to generate this all the time. And the discriminator will have a little bit of trouble with that because that example is included in both the training data and your testing data, and your generated fake data. This is not the ideal solution, but you can kind of get stuck in this place and it gets very hard to get out. So you get something that always generates one image or always generates one sentence or something like that. So there are ways to prevent this. One solution is basically you can use the other elements in a mini batch as side information for the discriminator. And what this allows you to do is basically say, you can look at the other generated elements, and if it starts generating things that all look the same, the discriminator will be able to say, wait, all of these look the same. They must all be fake. And that helps prevent it from generating the same sentence or image all the time. And then there's also other methods for this as well. Another problem for training is overconfident discriminators. So at the beginning of training, it's often very, very easy to tell the difference between generated and fake examples. So one way to fix this is label smoothing. So I think I talked about label smoothing here before. I don't remember. Did I do that? No? Maybe not. Okay. So the idea of label smoothing is normally normally when we do a prediction task, we're optimizing the probability of y, where y equals I. And I is the correct answer here. So normally we optimize the probability of the correct answer. The idea behind label smoothing is the model will become overconfident in predicting the correct answer. So instead of directly predicting, if we have a distribution over our choices, instead of trying to optimize the probability where the probability of the correct answer is 1 and all of the others is 0, we actually change our target to something where we add a little bit of probability to all of the other ones. So then we try to predict our correct answer with 95% confidence and all the others with 1% confidence, for example. And what this does effectively is this basically prevents your model from being too sure about its predictions and kind of spreads out your confidence over other predictions that you could make. Sorry, that sentence adds halfway through. And this one, they basically propose doing this over only one side. I believe this was smoothing the predictions over the real side, although I'm not entirely certain. Yeah.
So if the curve has to train GANs, the algorithm of the discriminator just a scalar probability. So how can we apply those things? Because we don't have one labels.
You have two labels. You have real and fake. So basically what you do is, instead of trying to predict the correct label with 100% confidence, you try to predict the correct label with 99% confidence. And if you get over that, then you stop. So this idea of label smoothing, this is useful in general, and it's quite easy to implement. So that's also something to work. We and Paul, who I work with, has found that this seems to work quite well, and a couple other papers have figured this, have used this in NLP tasks. Okay. So that's the overview of GANs. Now I'd like to talk about applying GANs to text. Are there any other questions so far? Okay. So there's a couple of applications of GAN objectives to language. So there's GANs for language generation, GANs for MT, GANs for dialogue generation. So this has been a very popular topic nowadays, and I think rightfully so. It's it's a nice model, but there's a very big problem. So the reason why GANs weren't applied to text immediately is because there's the very big problem that we're all familiar with now, which is that we cannot backprop through discrete. Discrete decisions. So specifically here, when we convert with the generator and generate X fake, this is a sequence of discrete symbols, so we cannot backprop through it. But luckily, over the past 2 classes, I've past 3 classes, I guess, I've talked about a whole bunch of different ways to solve this problem. So actually, just applying these methods that we use seems to be relatively effective for solving these. So as I said, there's a bunch of papers, but I'd say the great majority of them, they use policy gradient, like reinforcement learning type methods or minimum risk training type methods that basically do sampling and then treat the discriminator loss as a reward and then backpropagate that appropriately according to, and then use that appropriately according to the reinforcement learning paradigm. A second example uses a kind of adversarial objective with the reparameterization trick for latent variables using the Gumbel. I believe this was the Gumbel straight through or Gumbel softmax estimator. I forget exactly which one it was using. So you can also use the reparameterization trick that I talked about last time. So because I've already talked about these, I'm not going to talk about them in detail. They're almost exactly the same as the other ones. The one thing that you need to think about is discriminators for sequences. So how do we train a discriminator over sequences to decide whether it's a real-looking sequence or not? And here, the important thing is basically that this is just it's basically just a sentence classification problem. If we're creating a generative model for text, then this is just sentence classification saying whether this is a real text or this is a fake text. And we already know how to do sentence classification. So CNNs are the best way of doing sentence classification at the moment. They're the most accurate. They learn most quickly. So, so in general, methods have been using CNNs. Note that this is just, when we're using regular CNNs, this is methods that would be generating a single output, X. Often we'll also want to use GANs or something that looks a lot like a GAN when we're taking in an input X and we would like to output an output Y. So for like machine translation or dialogue response generation or something like that. So if that's the case, it gets a little bit more complicated, but not a lot more. So in maybe the fourth or fifth class, maybe the 5th class here, when I talked about CNNs, I also talked about methods for CNNs over pairs of sentences. And CNNs over pairs of sentences can also be, there's lots of different models of pairs of sentences used in like natural language inference, paraphrase generation, etc. One example from this paper by Wu et al. Is basically a thing where they kind of tile the word embeddings of the source sentence in the target sentence, and run this through a CNN that's more like a 2D CNN, more like a CNN that we would use over images as opposed to a CNN over 1D text. So this model actually is really difficult to understand until you figure out what's going on, because they're doing something that seems a little bit strange. But basically the idea here is we have 2 sets of vectors. The vectors in the back of this tensor are the target vectors. The vectors in the front of this tensor are the source vectors. Then the source vectors are distributed over rows, and the target vectors are distributed over columns. So what this basically means is that actually the target vector, you multiply this n times, where n is the length of the source sentence. And the source vector, you multiply m times, where m is the length of the target sentence. So basically, you're duplicating these vectors, so you get all pairs of vectors aligned together in a single vector in the CNN. I think if you look at this picture for about 2 minutes, you'll be able to figure out what's going on. Or you can look at the paper. But basically the idea here is that if we arrange things in this way, we can get a relatively good thing that looks at both the source and the target and tells us whether this looks like a real generation result or a fake generation result. Any questions about that? Okay. So, actually, maybe I should have wrote GANs for text are harder. So GANs in general are pretty hard to train. Like I said before, they have the mode collapse problem and various other problems. GANs for text are even harder than that because you have all the problems that come with applying neural networks to text. Specifically, this paper was a very nice paper in that they showed all their hyperparameter values and they did kind of an ablation over various types of hyperparameters. And none of the hyperparameters worked except the one that they finally reported as their proposed model. So this is better than other papers on neural networks where you try a whole bunch of parameters and only report the one that works. This one, they reported all the ones that don't work also. But basically, they tried different types of discriminators. They tried a discriminator that used a CNN, one that used an LSTM, and one that used a bi-LSTM, and only the CNN happened to work here. They also did a thing where they trained the discriminator so that it would get a certain level of accuracy. And based on that certain level of accuracy, they found one where they trained the discriminator until it had about 0.8 accuracy, was perfect, and all the other ones failed. So if you're going to apply GANs to text, you should definitely do this, yeah.
So does this mean that they stopped the training when it got exactly 80% of the training?
I think that's basically what they did. They trained it until it got accurate enough, and then they stopped the training. I don't remember the exact schedule they used, so looking at the paper. Yeah.
This accuracy is on the training data set?
Yeah, this accuracy is on the training data set. Another example of GANs for text are hard is you need to be careful with your learning rate. So this is a different paper where they tried different learning rates. And the learning rate for the generator was really important. So the perfect learning rate gives you good accuracy. The too low a learning rate doesn't learn anything, and too high a learning rate fluctuates all over the place and doesn't do well. On the other hand, for the discriminator, they found this was not very important. It was basically the same for all of them. So one thing I should note here is that these papers were written with basically 2016 GAN technology. The GAN technology in 2017 is better. I'll talk about some at the end if I have some more time. So I think people are learning to be a little bit better at how to train GANs now. So some of these results are a little bit less true, but still it's something that you should be very aware of. Yeah.
Does the learning rate also depend on the number of parameters you have for your generator and discriminator?
Yeah, the learning rate always depends on a lot of different factors, and there's no, perfect way to choose your learning rate at the moment. So it's something to be aware of, and if you're not getting good results, if it's fluctuating, your learning rate might be too high. If it's not learning anything, your learning rate might be too low. So it's just something you need to try. If you have a whole bunch of hyperparameters and you don't want to try everything, there are good libraries for kind of automatically tuning your hyperparameters for you using stuff like Bayesian optimization. Bayesian optimization is like an automatic hyperparameter tuning technique. Other people have said random search, just randomly setting all your hyperparameters is a pretty good alternative to Bayesian optimization. So if you don't want to bother with tuning all of them, you could let something like that run for a while and then see which one ends up being good. So. Yeah, any other questions? Okay. So there's a couple tricks that people have used to stabilize GANs for text. One is with regards to credit assignment. So basically credit assignment, like in reinforcement learning, is a problem in GANs as well. What you know from a GAN is basically whether your discriminator said this, whether your discriminator said this sentence looks real or not. So it's exactly like a reward in reinforcement learning that you only get at the end of the sentence. And in reinforcement learning, credit assignment is a problem. You don't know which word was bad and caused it to make that prediction. So, so one solution is to do something that assigns reward for partial sequences. So, for example, if we have this, at the beginning of our sentence, we run our discriminator over this and get a discrimination score, basically. And maybe the discrimination score is pretty low because this looks like a reasonable start of the sentence. Then you do it over this is, you do it over this is a, and then you do it over this is a fake. And the moment it sees fake, it knows it's a fake sentence and gives a bad discrimination score to it. So then your model basically knows that the moment it started generating the word fake, this was a bad idea and it should have generated something else. So this is one way that you can kind of avoid this, this credit assignment problem. And then maybe sentence doesn't change anything at all. There's another stabilization trick. This was on like the first paper that people proposed for applying GANs to text. I think I have a reference, maybe I don't. So instability is a problem. So one way you can fix this is basically by doing multiple rollouts. So the idea is you start search up to here, and then this is your state. And then basically you start from a particular state, and then you roll out and do a whole bunch of generations, and then you run a discriminator over all of them and kind of compare the reward between them. And this is another way to make things more stable, like it was a way to make things more stable for reinforcement learning. So this is kind of an interesting application that's not the original. It's not the original reason for using GANs, but it was one thing that people have tried using it for. And basically, the discriminator tries to find the fake data. So what about the real data? What about the real data? Or what about the real data it marks as fake? So this might be noisy data. So they tried to select the data in the order of the discriminator score to do this. They said it's better than selecting data randomly. I don't know how useful this is in general, but it's something to think about. So okay, so that was the talk about generative adversarial networks. The next one is about adversarial feature learning. So just to contrast these, in generative adversarial networks, you have your X, which gets a hidden state, extracted features, and you generate Y, and then you use an adversary to basically say whether Y looks real or fake or not. And this is good because it lets you generate real-looking outputs. But another very nice way of doing learning is basically you create an adversary over this H here. So this is saying the features you extract from X need to satisfy some property that we learn using an adversarial objective. So why would you want to do this? There's a couple reasons. Sometimes you have non-generative tasks. So let's say you have a sentence classification task. This is not a generative task. You don't generate you don't generate an output that could be decided as real or fake. Another reason is continuous features are easier to optimize for than discrete outputs. So discrete outputs have all the problems that I talked about before, sampling, et cetera, while continuous features are easier to optimize. So one example of this has been, this is a recent paper, but it's actually quite popular now as a way to do things. But basically, if we want to do sentiment analysis or some sort of classification over a whole bunch of different domains, we basically don't want our model to be fooled by specific words in that specific domain. So the idea is we have a network where we take our input X, and we basically do our feature extraction up to get feature F. And then after this, we have our label predictor, which is kind of a neural network that predicts, does classification or does any other sort of task. But then on the bottom, we have a domain classifier. So this domain classifier will try to predict which domain this data came from. And if the domain classifier is effective at doing this, then it will, if the domain classifier is effective at doing this, then that means we're learning domain-specific representations, which is bad. So we basically flip the gradient and penalize the feature extractor anytime the domain classifier is successful. As I was doing a survey for this, I found this paper, which is kind of an interesting application of this, which is basically saying, let's say we have an application where we want to deploy a system, but we don't have enough training data. One thing we can do is we can generate training data, fake training data, and train our classifier on this fake training data, but we also have a small amount of real training data. So we want the adversary to basically make sure that our synthetic, the features extracted from our synthetic training data aren't any different from the features extracted from our real training data. So it's a nice way to apply this to tasks where we can generate data. They also had another thing where they had some data that was older than some other data, and they trained a discriminator, so you couldn't discriminate between those as well. There's other examples of learning language invariant. Sorry, go ahead.
In the previous slide, how can he get the domain label in that model?
Oh, we assume it's given. So like, let's say we're doing sentiment analysis over Amazon reviews. We know what category the review belongs to. So we have the label. If you don't have the label, I don't know if you can do this. You might be able to train a classifier on a small set of labeled data and then use that as your true labels, but yeah.
But isn't having the ability to get a domain help the generation process to generate out-of-domain things as well?
No, not necessarily. So like one interesting way to think about neural networks is, in general, is neural networks are feature extractors. And if you think about what feature extraction means, basically it means finding things that are relevant and throwing away everything else. So you don't, if everything in the text was relevant, you wouldn't even need a feature extractor. You could just take all of the text and input it into your classifier and then use it as is. But the reason why we do feature extraction in the first place is to kind of find the relevant information. And what this is telling us is some of the information that you're finding is actually not relevant. Like we want to remove the information about the domain because we know that's not going to be relevant when we make our classification decisions. And by giving a little bit of extra supervision about what is relevant and what is not relevant, you learn things that generalize better to unseen data, is the kind of interpretation, I guess. Of course, if domain label and class label are highly correlated, then this is a bad idea. This is only a good idea when domain label and class label shouldn't be correlated significantly. Any other questions? Yeah. Okay. So we can do a very similar thing for learning language invariant representations. So this is like exactly the same figure. The only difference is now they're classifying English or Chinese. So you have training data in English, you have training data in Chinese, and you try to discriminate between English and Chinese, which language this came from. The idea is exactly the same. It's exactly the same, but it's a little bit more ambitious, I guess, because the difference between domains is not as I guess the difference between domains is not as big as the difference between languages. So it's not it wouldn't be entirely clear a priori that having an adversarial objective like this would work, but it actually does work quite well. This is a plug for my own paper. It also works on machine translations. So if you want to train a machine translation model with multiple languages as input, it works to have an adversarial objective that tries to prevent the representations from being different in both languages. So similarly, we can apply this to multitask learning. So this is a little bit trickier than the other ones. So the previous ones here, these are straightforward applications of the previous one. Basically, we're taking the whole representation and trying to discriminate with it. The idea behind adversarial multitask learning here is some tasks should share some features. So maybe some features are relevant for both sentiment analysis and I don't know, and topic classification or something like that, but some features are not. And the idea here is you can train a model where some of the features are shared between the two tasks and some of the features are not shared between the two tasks. But you basically can't, if you just train the model as is, some of the stuff that's relevant to both tasks will leak into the kind of private representations, and some of the stuff that is not relevant to both of the tasks will leak into this kind of shared representation that both of the tasks use. So what they do is they basically have this adversarial shared private model where what they do is they have an adversarial discriminator on the shared features to try to push them together. Then they have orthogonality constraints on the separate features to make sure that they're capturing different information from each other. So we don't want the private representations to be similar. So you try to force them apart, basically. And this is a kind of this is the last slide on adversarial feature learning, but it's not really learning features so much. It's kind of a very clever application, I thought, though. And the idea is basically that in discourse parsing, which we're going to talk about maybe next Tuesday, or Hector's going to talk about next Tuesday, you have an idea of discourse connectives or discourse relations. And discourse relations are often marked by explicit discourse connectives. So what we mean by an explicit discourse connective is something like because. And that's, you have one sentence and then you have because. And then you also have sentences that don't have any explicit discourse connective, but they still have a discourse relation. and you try to generate representations based on both of these sentences, and you want the representation for the one with the explicit discourse connective to be very similar to the one without the explicit discourse connective. So I never thought about using things like using a adversarial objective in this way, so I thought this was a pretty clever way of using things. So if you have a similar problem where sometimes your information is explicit and sometimes your information is not explicit, then something like this might be something useful to use. Oh, this was work done partially by people here at CMU and partially by people other places. Okay, so that's it for the adversarial feature learning. Are there any questions? I only have 2 more slides, so we might finish a little bit early today. Okay, so I will move on to the next one. This method is it's very much a mix between adversarial objectives on the outputs and adversarial objectives on the features. I think it's a kind of clever idea also, and it gets around the problem of having to make discrete decisions in your output generation. And yeah, it's halfway between a discriminator on discrete outputs and feature learning. So the basic idea is this is for when you want to generate a sequence of tokens, like in text generation or machine translation or whatever. So what you do is you generate the output sequence according to the model, but you train the discriminator on the hidden states. So what that looks like is basically this is your generation process. You take X and you generate Y according to an RNN or whatever. But instead of applying the adversary to Y, you apply the adversary to H directly. And because H is a continuous vector, you can apply an adversary directly to it without worrying about your sampling decisions, etc. So the idea is quite simple. One interesting application of this is that this was used for unsupervised style transfer for text. So if you want to transform text from one, basically from one language to, not one language, sorry, one style to another, then this is a method that you can use. So they have 2 potential styles. One is, for example, like one is positive and one is negative sentences. And they use a professor forcing objective to basically discriminate between sentences where you have the true style being 1, or whether it's a sentence where you have the true style 1, or whether it's a generated sentence where you have 2 to 1, style 2 being transformed into style 1. And then you have another discriminator for vice versa. So you basically have one discriminator that tries to discriminate between true and fake style 1, true and fake style 2. Oh, sorry, I forgot one very important thing. So if you just did this, then it would be easy to fake, just randomly generate a sentence of style 1. But they also have an objective where you need to map back. So it's kind of like an autoencoder type objective to make sure that you can restore your original sentence as well. So these 2 are balanced together. And they have some interesting examples of this mapping from negative sentence to positive sentence. Like, I would recommend find another place because I would recommend this place again, which is actually pretty funny because it has like, find another place and again, you have the like repeating thing here. And then do not like it at all. All in all, it's great. I regret not having the time to shop around. I have a great experience here. Then you also have average Mexican food becomes authentic Italian food. So there's still there's still some future work to be done here. But given that this is unsupervised, I think it did a pretty good job. So that's about all I have. I think there's a lot more potential applications for this. If you're doing something like this, I think a lot of people are interested. So I would urge you to try to come up with kind of creative ways to use things, as opposed to just applying it to your problem. But I think it's a really nice tool to have in your toolbox if you want to do something. Any other questions or things? No? Okay. It's a little bit early, but I'll finish up here. Thanks a lot.